Recording now, and then I will be careful during the break because in the last in our last lecture after the break I kind of forgot to restart the recording. But anyway, so for the second part of the last lecture, I got the video from last year and I put that on Moodle as well, so that you guys have the material recorded anyways. But today I'm not stop the recording anymore to avoid that I make this mistake again. So in the Moodle page, you have the recordings for the lectures there. All the slides are ready, and also the first homework, which is due next Friday. So as I mentioned, I will give you guys 2 weeks for each homework. And after we finish our discussions of acids and bases, which should take place on Friday, probably there will be another homework coming as well. So homework 2 will also be released probably by the end of this week. Let's see how it goes. All right, so hope everybody had a great weekend. And now it's Monday, a great day for some inorganic chemistry. So today we will continue our journey throughout our inorganic chemistry course, and then we will start to cover acids and bases, which takes part of the first part of our course, which is dedicated to the chemistry of the elements. So the goal is to finish these discussions of acids and bases today and on Friday. So we will have 2 lectures covering acids and bases. So the agenda for these classes are to discuss definitions and concepts, or the different definitions of acids and bases that are found in the literature. Then we will focus on the Bronsted acids, or the Bronsted-Lowry theory of acids and bases, and we will discuss some periodic trends on acid and base behavior across the periodic table. Then we will discuss the formation of simple oxo acids, anhydrous oxides, and polyoxo compounds in the framework of acids and bases. Then we will focus on the Lewis theory of acidity and basicity. So we will discuss Lewis acids and bases, group properties, and some important reactions that these species can undergo. And then we will also cover several factors that govern interactions between different acids and bases, and we will see that this acid-base interaction is very important to understand the formation of several inorganic compounds and also to predict the outcome of several types of reactions. And then we will end our discussion by presenting the soft-hard classifications of acids and bases and the thermodynamic acidity parameters. And then we saw a little bit of this acid or about these hard, soft interactions in our previous lectures. And then we will see this in more detail here in the framework of acids and bases chemistry. All right, so why do we study acids and bases? Actually, acids and bases play a central role in chemistry, but not only in chemistry, but in other sciences as well. Acids and bases are crucial or central for several chemical processes, including various natural phenomena, processes in several industries, relating chemical conversions and catalytic processes, several biological processes as well. So acids, we can definitely say that acids and bases are essential not only in chemistry, but in our world and our life. For example, the concepts of acids and bases are important for, like, it dictates the time for a metallic object to dissolve in acidic media. It dictates the ability of the aquatic environment, for example, to support life. And also acids and bases are involved in reactions that control and sustain our life. and this involves the reactions that stores and releases energy in our body. So acids and bases have been studied since the beginnings of the field of experimental chemistry, and they have been recognized since ancient times based on their properties. For example, acids coming from the Latin acidus, which comes from sour, bases from the Old English to bring down or to bring low, the base. And then, so actually in the beginning of experimental chemistry, we even recognize this species by tasting it, which is kind of crazy if we think about it like in recent days. And it was only in 1880 that we had the first like proper definition of acid and base. And this was proposed by the chemist savant Arrhenius, which then proposed that acids are species that, when dissolved in water, increase the concentration of H plus ions. So this is the Arrhenius definition, which is the simplest, maybe more well-known definition of an acid and a base. So therefore, using this same reasoning, a base is a species that, when dissolved in water, increases the concentration of OH minus ions. So for example, here we have hydrochloric acid, which is an Arrhenius acid, because here in this case, when dissolved in water, it increases the concentrations of H plus ions. So here we can already see that in this definition involves dissolved in water, which means that the concept of Arrhenius acids and bases are limited to solutions prepared in water. So limited to aqueous solution. So this is one of the main limitations of this simple but efficient definition. In this context, two scientists, Bronsted and Lowry, then proposed a more generic definition of acids and bases, which consists on the following: that acid-base reactions involve transferring of H plus ions from one substance to another. So this is the core of this more generic definition proposed by Bronsted and Lowry, or the core of the Bronsted-Lowry definition of acids and bases, because they propose that these acid-base reactions involve the transfer of H plus ions. So for example, H plus in water leads to the formation of H3O plus, as shown here. So we have H plus in water leading to H3O plus. And then actually these species can form even higher structures, having like more water molecules located or comprising the interaction between more water molecules. So H3O plus can turn into like the formation of H5O2 plus, and H9O4 plus can also be observed by these interactions of H plus and water in solution. But anyways, in this case, what is important that is in this definition, acids and bases involve reactions in which the proton H plus is transferred. So if we look at this, like as we were talking about the Arrhenius definition for HCl, like HCl dissolved in water, this is the way that we wrote the equation for this process to take place. But according to the Bronsted-Lowry definition, or in the Bronsted-Lowry framework, we can write this process by this kind of equation here in this case, in which we have HCl dissolved in water, so HCl reacting with water in a proton transfer reaction in which the proton from HCl is then transferred to water. This generates then chlorine ions plus H3O plus, in which the hydrogen that was here bound to the chlorine atom then is transferred to water. So we can see that therefore, this reaction in which HCl is dissolved in water can be regarded as a reaction, a proton transfer reaction in which the proton is transferred from HCl to water. So in the definition of Bronsted-Lowry, an acid, therefore, is a substance which can be a molecule or an ion that donates a proton to another substance, another molecule or ion. So acids is a species that donates a proton, and bases are a substance that receives the proton. So in this kind of reaction that we just saw, then the HCl is the acid because it's donating the proton to water, and then water is the base because it's receiving the proton from the acid. So in this case, HCl can be seen as the Bronsted-Lowry acid, while water was the Bronsted-Lowry base. And what is important is that this definition, therefore, is not, because it involves the concept of proton transfer, or the definition is based on the concept of proton transfer. This means that this definition applies also to non-aqueous solution and also to reactions occurring in the gas phase, such as the reaction of HCl and ammonia. So in this case, HCl, or hydrochloric acid, donates its proton to the ammonia molecule, generating Cl- and ammonium ions, so NH4+. So we can see that therefore HCl is the acid because it donates the proton, while ammonia is the base, as ammonia receives the proton from the acid. So for example, if we look at this reaction of ammonia in this case and water, right? We can see that ammonia can be classified as a base, and then we can use the definition of base of both Arrhenius and Bronsted-Lowry to define the base here. So if we have an Arrhenius base, for example, an Arrhenius base will also be a Bronsted-Lowry base, right? Because a base, it will be a base in both theories. So for example, if we define the base here in terms of the Arrhenius definition, it means that the base, when dissolved in water, it increases the concentration of OH ions in solution. However, based on the definition of Bronsted-Lowry, then the ammonia can be defined as the base because it receives the proton. So water donates a proton to ammonia, generating the ammonium ions and OH minus. So it's a base in the concept of Bronsted-Lowry, as it accepts the proton from water in this acid-base reaction. Okay, one important feature of these proton transfer reactions between acids and bases is that this reaction can be fast in both directions, which means that the dynamic equilibrium or the chemical equilibrium here can give, for example, a more complete description of the behavior when we are dealing with acids and bases that are weak. For example, HF and ammonia, then just writing the forward reaction alone. And therefore, one of the central features of the Bronsted acid-base chemistry in aqueous solution is that we have that the species attain or reach chemical equilibrium for the proton transfer reaction very quickly. And here, if this equilibrium is more shifted to the formation of the products or more shifted towards the reactants, this will determine if the acid or base is weak or strong, as we are going to see in the following slides. So in this, like taking a look at this definition of acid base as a proton transfer reaction in the Bronsted-Lowry definition, as we are studying and discussing here. So we have here another example of an acid-base proton transfer reaction in which HNO2 is the acid because it donates electrons to water, which is the base because it receives electrons. So this is an example of this acid-base reaction. So in this context, when the species donates a proton, which is the acid here, when it donates the proton, it becomes a molecule or a species with one proton less. So this, in other words, the acid, after removing, when it donates a proton, we have the formation of a conjugated base. So the acid leads to the formation of the base after it loses one electron and one proton. And the same thing occurs for the base. The base, after receiving a proton, will become a conjugated acid. So in an acid-base proton transfer reaction between an acid and a base, the acid will become a conjugated base after it loses or donates the proton, and the base will become a conjugated acid as after it receives a proton. So if we look at the reaction on the reverse direction, this species, the conjugated acid, will act as an acid, and the conjugated base will act as a base. All right, so the conjugated base of an acid is the species that is left after the proton is lost. So proton, after the proton is lost, then we have the conjugated base. And the conjugated acid of a base is the species formed when a proton is gained. So the conjugated base formed when the base gain a proton. So for example, fluorine ions is the conjugated base of hydrofluoric acid, and H3O plus is the conjugated acid of water. So like fundamentally, there is no distinction between an acid or a conjugated acid and a base and a conjugated base, because a conjugated acid is just another acid and a conjugated base is just another base. Okay, so let's identify now who is the Bronsted acid and its conjugated base in the following reactions. So the first one, who is the Bronsted acid? So the first one is here, this reaction. The acid is the species that donates the proton, right? So here we have that this proton is being donated to OH minus, generating water and sulfite. Yes, good, Adam, right answer. And then, so this is the Bronsted acid, and then its conjugated base will be sulfate. Okay, so for B, we have this reaction, so we can see that the proton is being transferred from water to phosphate. Therefore, water is acting as the Bronsted acid, and then OH minus is its conjugated base. So is that clear for everybody? If not, let me know. Okay, so this is the main definitions, and now we can start to analyze the relative strength of Bronsted acids and bases. So, okay, so let's start with Bronsted acids. So the strength of a Bronsted acid is measured by the acidity constant, and the strength of a Bronsted base measured by the basicity constant. So this is an important concept. And another important concept is that the stronger the base, the weaker is the conjugated acid, and the stronger the acid, the weaker is the conjugated base. And then also for measuring these strengths, and an important parameter here is the pH, which is defined by the minus log of H3O plus. And this will be important in the discussions of acids and bases as well. So, okay, so I mentioned that the strength of a Bronsted acid is measured by its acidity constant. So what is this acidity constant? The acidity constant for several acids, here using HF as an example. So the acidity constant is given by this expression. So to get here, what we do is we write the acid-base reaction for this acid with water, in which the acid in question, HF, here in this example, acts as an acid in a proton transfer reaction with water. So this is the expression. Therefore, the acidity constant refers to the equilibrium constant for this reaction. So it's equilibrium constant for this reaction. Therefore, it comprises the concentration of H3O plus times the concentration of fluoride divided by the initial concentration of HF. So the stronger the acid, the higher is the acidic constant, which means that the reaction is more shifted towards the formation of the ions. Therefore, the concentration of these species will be higher than the concentration of the initial acid. So this will be lower. So the reaction will be favored towards the direction of H3O plus and F minus. So for a generic acid here, HX, for example, the acidic constant has this kind of form. And for the bases is the same thing. The basicity constant can be written as the equilibrium constant for the reaction of the species of interest, in this case ammonia as an example, acting as a base in a proton transfer reaction with water. So the equilibrium constant for this reaction is concentration of ammonium times the concentration of hydroxyl ions divided by the concentration of ammonia, or more generally for any base, this format. And again, the higher the strength of the base, the higher is the basicity constant, which means that the reaction is shifted towards the formation of the ions. So the concentration of Hb plus and OH minus is higher than the concentration of the base in solution. Regarding water and some other species as well, water can have a behavior that it's called amphiprotic. That in this case, water can act both as an acid or as a base, depending on the situation. And also in this case, water, because of this amphiprotic behavior, a proton transfer equilibrium between water molecules can exist even in the absence of added acids and bases. So we can have proton transfer from one water molecule to another, and this process is called autoprotolysis or autoionization, and it's given by this expression in which water to a proton transfer can take place between different water molecules. So we can write an expression for the autoprotolysis constant for this reaction, having this form, and this corresponds to 1 to the minus 14. But also, this means that we can deduce this expression as well, which for an acid and a conjugated base, the product between the acidity constant and the basicity constant is equal to this autoprotolysis constant. Okay, so this is a diagram showing various acids and their different kinds of strengths. So we can hear that the acid strength for these acids that are shown in this diagram increase in this direction. And here we have the corresponding conjugated bases for these acids, and we can see that the strengths of the bases increase in the opposite direction, which illustrates that the stronger the acid, the weaker is its conjugated base. And the weaker the acid, the more strong is its conjugated base. And for bases, is the same thing. The stronger the base, the weaker is the conjugated acid, and the weaker the base, no, the stronger the base, the weaker is the conjugated acid, and the weaker the base, the stronger is the conjugated acid. Another important concept is that we can also have polyprotic acids, which is acids that can have that can donate more than one proton in a proton transfer reaction. So a polyprotic acid loses protons in succession, and successive deprotonations start to become progressively less favorable. So the definition is that a polyprotic acid can donate more than one proton in a proton transfer reaction. One example here, hydrogen sulfide, which is a diproic acid because it can donate 2 protons in the proton transfer reactions. So here, in this case, if we have a diprotic acid, we can have 2 proton donations and two acidity constants. So here we have the expressions or the proton transfer reaction for these two proton reactions. So first of all, hydrogen sulfide can transfer the first proton to water through this expression, and for this we can have the first, from this reaction we can write the first acidity constant for the first proton transfer reaction, and then we can have the second proton transfer reaction according to this equation, generating sulfide ions and H3O+, and then for this we can write the second acidity constant for the second proton transfer reaction according to this equation. So if we look here at the magnitude or the numbers for the first acidity constant and the second acidity constant, we can see that the second acidity constant is significantly smaller than the first acidity constant, and this is true for all acids normally. So normally, the second acidity constant is always almost smaller than the first one, and then if we have more like acid triprotic, for example, or if an acid can transfer 3 protons in a proton transfer reaction, for example, then the third will also be smaller than the second, and so on. So why is this second proton transfer acidity constant smaller? So the second, the protonation is always less favorable, or it has a lower acidity constant, because in the second case here, H, the proton, has to be transferred from an atom or from a species that has one more negative charge than in the original first, the protonation. So here we have one additional negative charge. So here we didn't have any negative charges, and here we have a negative charge in the species. So therefore, this means that because of this negative charge, we need additional electrostatic work to remove the positively charged proton from a negative charge species. So in other words, the proton becomes much more difficult to be transferred because it's more strongly bound to the molecule because of this electrostatic interaction between caused by this negative charge. So here we have the acidity constant for several types of acids. As an example, and also the pKa, which is minus log of Ka. So here we can see like the relative strengths of all these different species. And then we will check and understand why we have these differences in strength for several of these species based on periodic properties. Okay, so when we are talking about the strengths of Bronsted acids, and we are talking about polyprotic species, either polyprotic acids and polyprotic bases as well, we can write, like it's a useful thing that you may frequently see in books and literature in general, a distribution diagram, which comprises a representation of the concentrations of several species that are formed during these successive proton transfer reactions coming from a polyprotic acid or a polyprotic base. So this distribution diagram usually show the fraction of a species as plotted against the pH, so show the fraction of the solute present as, or the fraction of one of the species as a function of the pH. So if you take a look, for example, at phosphoric acid, which is a triprotic acid, so these species can donate 3 protons in a proton transfer reaction with water, for example. So the species that can be formed are the initial acid and the product after the first proton transfer reaction, after the second proton transfer reaction, and after the third proton transfer reaction. So here actually there is a mistake here in the charges. So therefore we can calculate, like in this case specifically. So there is the formation of all these kind of species. So if we want to know the fraction of the solute present as the initial acid or H3PO4, we can use this kind of expression, which is the concentration of the acid divided by the total concentration of species in solution. So that's why is the fraction. So we can calculate this as a function of pH for all the species. So for H3PO4, we have this kind of curve. So for H2 PO4 minus, we have this kind of curve. So make sure, pay attention that these different curves here have different colors. You can check in the class notes afterwards and so on. So therefore, in these kind of distribution diagrams, we can have the concentration of, we can plot the concentration of each solute or each one of these different species at a given pH. And then we can calculate this from the pH and pKa values. So for example, here we have pKa1, pKa2, or pKa3 as a function of the overall pH. So if the pH is smaller than the first, than pKa1, this corresponds to very high hydronium ion concentrations because the pH is small. And this means that in this kind of region, the dominant species is H3PO4, so the original acid. And on the other hand, if the pH is higher than pKa3, which is this region here, this means a very basic solution, so low hydronium ion concentrations, and therefore the dominant species become the phosphate ions. So based on the diagrams, we can predict, based on the pH, which will be the dominant species in solution. Okay, so after we saw these main definitions or how we can know from the acidity and basicity constants what acids are strong or what acids are weak and so on, we can discuss what are the main factors that dictate the strengths of bronze acids and bases. So if we take a look how we can understand why some species are strong acids while other species are weak acids, for example, we can get a better understanding or a quantitative understanding of how strong an acid is, or the relative acidities of protons bound to an atom, or expressed by XH here. So the understanding of these relative acidities can be obtained by analyzing the enthalpy changes that follow these proton transfer reactions, because the enthalpy changes will tell us how easy or how strongly bound this hydrogen is to this atom, and this will dictate how easy the proton can be transferred in a proton transfer reaction, and this will therefore dictate the strength of the acid. So if we take a look at a proton, the simplest reaction of a proton is the attachment of the proton to a base, here represented as A-. So we are representing this as A- here as a negative charged species, but this could also be a neutral molecule such as ammonia, as we shown as an example here several times. So the simplest reaction of a proton is its attachment to a base, right? So the enthalpy for this reaction is the proton gain enthalpy. So this reaction, the enthalpy of this reaction is the proton gain enthalpy. And the negative of this quantity is reported as being the proton affinity, right? So the negative of this proton gain enthalpy is the proton affinity of the species. All right. So if the proton gain enthalpy here for this transformation, the attachment of the proton to a base. So if the proton gain enthalpy is large and negative, This corresponds to an exothermic proton attachment, and this means that the proton affinity is high. So if the proton affinity is high, this means that this reaction, the attachment to the proton of the base is very favorable. And if this is very favored, this indicates a very strongly basic character for this species, right? Because if this species can receive the proton, and this is very favorable, and the proton affinity is very high, the basic character will be very strong, because according to the Bronsted-Lowry definition, a base receives the proton, right? On the other hand, if the proton gain enthalpy is only slightly negative, this indicates that the proton affinity is low. So if this species has a low proton affinity, this will be like a weaker base, because the base has to receive the proton in a proton transfer reaction according to the Bronsted-Lowry framework. So therefore, a weaker basic character means a more acidic character in this case. So proton affinity, if proton affinity is high, we will have strong basic character. If proton affinity is low, then we have acidic character or strong acid. So if we take a look at the proton affinities of the conjugated bases of some p-block binary acids HA, right? So we have here the acids and the conjugated bases, right? And then here we have the proton affinities. Here in this case, it's the proton affinity in the gas phase, and this the proton affinities in water. So what happens? We can observe, like, what can we see across the periodic table? So we can see that there is like the proton affinities here. So when we go like on a period, for example, from nitrogen to carbon, oxygen, fluorine, right? So like in general, what happens is that the proton affinity decrease to the right along a period, and down the group. So decrease to the right along a period and decrease down a group. So if the proton affinity decrease to the right along a period and decrease down a group, these are the regions in which there is a decrease in basic in basicity, and therefore in this direction there is an increase in the acidity, right? Therefore, we can observe that HF is a stronger acid than water, right? So from HF to water, or if we take a look at the bases, like there is this decrease in the proton affinities to the right, along the right in the periodic table. So this means that HF becomes a stronger acid than water. And if you take a look just at the halides, HI is the stronger acid of the hydrogen halides. So in other words, the order of the proton affinities for the conjugated bases is that the proton affinity for the conjugated bases iodine is smaller than hydroxyl and fluorine. Okay, was that clear? All right, and these kind of behaviors can be also understood using this thermodynamic cycle to understand the origins of these kind of variations and trends based on these proton affinities, because in this case, this involves the enthalpy for the proton gain of the species. So the proton gain can be thought as the outcome of the 3 steps: electron loss for the base, the electron gain by this species, and the combination of the proton and the base here. So this is the overall kind of equation. So the reverse of electron gain by the base, the reverse of the ionization of H, and the reverse of a bond dissociation. So the proton gain enthalpy can then be understood in quantitative terms by the sum of these enthalpy changes, or the enthalpy changes of all these processes. Therefore, we can have that the proton affinity can be given by this kind of expression, involving the formation of the bond, the ionization, and the electron affinity here. So if we take a look at the variation along the period, the dominant factor in the variation in the proton affinity across the period is the electron affinity of the species. So the electron affinity increases from left to right, and then if the electron affinity increases from left to right, this lowers the proton affinity. So if the proton affinity decreases of this species, so proton affinity decreases, basic character basicity decreases, and therefore the gas phase acidity increases across the period as the electron affinity of this species increases. And because therefore the electron affinity correlates with increasing electronegativity, the gas phase acidity also increases as the electronegativity increases. So the acidity will increase together with the electronegativity. Regarding the trend across the group, the dominant factor descending our group is the decrease in the bond dissociation enthalpy of the bond between the proton and another atom. And the overall result of these effects is therefore a decrease in the gas phase proton affinity when we have an increase in the gas phase acidity of HA from left to bottom of the P block. Okay, so let's say this again. So like when we are going down the group, the dominant factor is the decrease in the bond dissociation enthalpy. So as we go down the group, the atoms get bigger, so the bond becomes weaker, so the bond becomes easier to break. If the bond becomes easier to break, it's easier for this proton to be transferred in the proton transfer reaction, and therefore acidity increases. Okay? So overall, if we take a look at these variations like down the group regarding the variation in the HA bond dissociation enthalpy and the variation in the proton affinities relative to electronegativities and electron affinity that we just discussed, the increase in the acidity, overall acidity, goes from top left in the periodic table to bottom right of the periodic table in the P block. When we have solvents, the solvent can, when we are not talking about the gas phase, solvents can provide additional stabilization by the role of the solvent, and this can change the trends in some cases. So therefore, we can see this overall trend in the strength of acids and bases across the period and across the group. So acid strength increases from left to right and increases as we go down the group. All right, so let's take a 10 minutes break now, and let's be back at 1:16. Is that okay? All right, I will see you guys at 1:16. Hello, everybody. So welcome back from our break. So now we will discuss some characteristics of Bronsted acids. In particularly, we will talk about aqua acids, hydroxyl acids, and oxo acids, and then we will see that they are typical of specific regions of the periodic table. And in this discussion, we will concentrate on Bronsted acids and bases in water only, and the largest class of acids in water consists of species that can donate protons from an OH group attached to a central atom. So in this case, in the context of inorganic chemistry, in the context of these aqua acids, hydroxyl acids, and oxo acids, so the largest class of acids are those who can donate protons from an OH group attached to a central atom. And a donatable proton of this kind, it's called acidic proton, to distinguish from other protons that might be present in the molecule. For example, the non-acidic methyl protons in this kind of molecule. So these protons are not acidic, while this is the acidic proton, or the proton that can be transferred in a proton transfer reaction. So we are going to consider first these three classes of acids, Bronsted acids, aqua acids, hydroxyl acids, and oxo acids. So first of all, let's focus on aqua acids. So here for the aqua acid, we have that the acidic proton is present in a water molecule that is coordinated to a central metal ion. So here, for example, is this coordination compound or complex involving iron coordinated with 6 water molecules. And one of these hydrogen atoms here on the coordinated water represents an acidic proton and can be transferred in a proton transfer reaction to generate to water, generating Ag3O plus and the species that is formed after the loss of one of these protons. So this is another representation of this aqua acid containing water molecules coordinated to this central ion, and then one of these hydrogens, protons, is the acidic proton. So here is an example, another example of this representation of the central atom with 6 coordinated waters, and then this is the acidic proton. So these are the species that are generated after the proton transfer reaction. And here is another representation of this process. So in which we have this aqua acid transferring one of the protons to water molecules, generating the species here after the loss of a proton and H3O plus. All right. The second class of acids is the hydroxyl acid. Here, the acidic proton is on a hydroxyl group without a neighboring oxo or oxido group. So here we have an example of hydroxyl acid in which the acidic proton is on a hydroxyl group without an oxo group in the molecule. So this is an example of an hydroxyl acid. So here only hydroxyl bound to the central atom. And the oxo acid in this case, in the oxo acid, the acidic proton is also present on a hydroxyl group. However, in this molecule or in this oxo acid, this hydroxyl group containing the acidic proton also possess like an oxo group attached to the same central atom. So this is the oxo acid. So here we have the representation of these 3 classes of acids, the aqua acid, the hydroxyl acid, and the oxo acid, and they can be regarded as successive stages in the deprotonation of an aqua acid. So the aqua acid, hydrogen in water molecules coordinated to the central atom. Then the hydroxy acid, acidic protons on hydroxyl groups and no oxo groups. And then the oxo acid, acidic proton on a hydroxide group. And then in this group, there is also an oxo group present in the molecule. So the distinction is important just because like the hydroxyl acid can lead to the formation of an oxo acid after a proton transfer reaction. So they represent different stages in the donation of a proton or the protonation of a proton. So the oxo acid is different in a way that it can gain one proton to become a hydroxyl acid, or a hydroxyl acid can donate a proton to become an oxo acid. So they are different in terms of protons that can be donated, and therefore acidity constants and properties. So In the case, like regarding the positions of or the main types of acids that form along these species on the different regions of the periodic table, we can see that for aqua acids are predominantly characteristic of species in which the central atoms have low oxidation state, represent S and D block metals, and also metals on the left of the P block, while the oxo acids are commonly found where the central element is in a high oxidation state. And this, for example, like an element from the right of the P block may also produce an oxo acid in one of its intermediate oxidation states, as an example here. All right. And when we talk about these aqua acids, their relative strength typically increase with the increasing in the positive charge of the central atom and with decreasing ionic radius. And this, like we can understand these trends based on the ionic model, in which the cation or the metal cation is represented by a sphere of radius R plus carrying Z positive charges. This means that the protons can be more easily removed from the vicinity of the cations with high charge and small radius, because this makes them more ionic, and then they can receive the electrons from the metal H bond more easily, which means that the protons can be released more easily. So if we have this, so for the release of the proton, we need this to take place, right? For example, and then if the species close to the forming the bond with the hydrogen has like the ability to receive this electron donation, this means that the proton can be more easily released, and this will be favored when the central atom in the molecule has small radius and high charge, because this will favor this process. You favor this process to take place based on purely an ionic model in which the positive charge, small and large charge of positive species will be able to attract this electron pair and therefore release the proton. So this model predicts that the acidity should increase with increasing charge and decreasing the ratio of the metal cation. So this was like for the aqua acids, and for the oxo acids, the simplest oxo acids are mononuclear acids, which contain one atom of the parent element, such as carbonic acid, nitric acid, phosphoric, and sulfuric acid. These oxo acids are formed by electronegative elements, so they are in the top right of the towards the top right of the periodic table, and by other elements also in high oxidation states. So here we have the structure and pKa values for some oxo and hydroxo acids, in which P here represents the number of non-protonated oxygen atoms. So here we have like the values for these different species, and then we can try to understand now why like there is these variations in the strengths of acids. Okay, so let's take a look at this now. So if we talk about these substituted oxo acids, right? And this is also this explanation that we will provide now it works for the oxo acids and also substituted oxo acids as well. So the strengths in these species can be rationalized in terms of the electron withdrawing power of the substituent. And also here, the strength of these acids, or oxo and hydroxyl acids, also can be predicted by these kind of electron withdrawing properties, or kind of an ionic model, in which was the same trend that we discussed previously, in which we can use this ionic model, in which the central atom, when it can when this central atom becomes more positive or more electron deficient, this will increase the proton transfer properties, so you'll be able to capture this electron pair more, and this will favor the release of the proton, so the species will become more acidic. Okay, so let's understand this for the substituted oxides, that will become easier to understand. So here is an example of a substituted oxo acid, for example. So these substituted oxo acids have strengths that may be rationalized in terms of these electron withdrawing properties of the substituent. So one or more OH groups of the oxo acid might be replaced by other groups to give a series of substituted oxo acids. So here in this case, one of these species, for example, the fluorine, can replace these hydroxyl groups, and here the sulfite. So here is one example with sulfite, and here we have ammonia as well in this species. So what happens is, when we have here the OH bond, right, the acidity, or the acidic proton comes from an OH bond. So if we have a species, or if this OH bond, or this oxygen atom, is then bound to another species, like here represented as Y, if the electronegativity of this species increases, it means that the electron density of this bond is shifted towards the more electronegative element. So if this is shifted towards the more electronegative element, this becomes more positive, and this bond becomes weaker. So in this case, this more positive part of the molecule can capture this electron density more easily, and therefore the proton can be more easily removed or more easily transferred from the OH group to water. So for example, taking a look at these two species, right, or these two oxo acids, because here we have fluorine, is highly electronegative, we withdraw electrons from the central sulfur atom, so this will become a little bit more positive, so has sulfur a higher effective positive charge. Therefore, this this acidic proton can be more easily released or more easily transferred, which indicates that this substituted acid will be stronger than the species only with oxygen. And then here, if we have just like the non-substituted oxo acid, we can also see that the strength or the relative strength here comes like we have the differences in electronegativities here, and then we have that the sulfur central atom also has an effective positive charge, as oxygen is more electronegative and withdraw charges from this species. So that's why this proton can be easily released or transferred and then this species is has the acid, its acidity properties. And this is also the reasoning that we can use for the non-substituted oxo acids. And we can have, so this electron acceptor or electron withdrawing groups that makes these oxo acids to become even stronger. But we can also have other groups such as N2 group, which has lone pair electrons that therefore, instead of withdrawing electrons, donate electron density to the central atom, which has the opposite effect, therefore reduces the positive charge on the central atom and therefore weakens the acid. So it becomes the acceptance of this electron density and therefore the transfer of the proton less favored. So there are some empirical rules that have been systematized by Pauling to systematize or to create an understanding on the strengths of a series of oxo acids. So for a series of oxo acids that contain a specific central atom with various numbers of oxo and hydroxyl groups, we can predict the strengths of these species based on these Pauling's rules. So for example, for a series of mononuclear oxo acids of an element E, the strength of the acid increases with increasing number of oxygen atoms. These strengths qualitatively can be understood based on the electron withdrawing properties of the oxygen. So oxygen are electronegative, withdraw electron densities, making the OH bond weaker, so proton easily released. So the more oxygen atoms, more withdrawing of electrons will take place, and therefore the acid will become stronger. And for any series of oxo acids, the one with the most oxygen atoms will therefore be stronger. So in this series, for example, this can be understood. So more oxygen atoms, more withdrawing properties from the central atom, hydrogen, acidic hydrogen, more easily released. And another important factor is the degree to which different numbers of terminal oxo groups stabilizes the conjugated base by resonance. For example, here we have the conjugated base of sulfuric acid, for example, which is the HSO4 minus ion, which can be described as a resonance hybrid of three different contributions as shown here. And for this, we have only two resonance distributions. So if the higher the number of resonance species, the higher the stabilization of that species, which means that HSO4 becomes a stronger acid than HSO3 minus. So these trends overall can be systematically understood by using two empirical rules that were devised by Pauling, in which P is the number of oxo groups and Q the number of hydroxyl groups in these acids. So for the oxo acid having this general formula, the pKa will have these values, and the successive pKa values of polyprotic acids will increase by 5 units for each successive proton transfer reaction. And these rules can be understood by inspecting this table below, in which the acids are grouped according to the number of non-protonated oxygen atoms. Okay, so these are the number of oxo groups. And then we can understand these strengths based on these electron withdrawing properties and these rules devised by Pauli. Okay, so we have treated so far these oxo acids as being derived by the deprotonation of their parent aqua acid. So the aqua acid leads to the hydroxyl acids, leading them to the oxo acids. It's also useful to do the opposite, to take the opposite viewpoint and consider these aqua acids and oxo acids as derived from the hydration of the oxides of the central atom. And this approach emphasizes a concept that we touched upon in the previous lectures, which is the acid and base properties of the oxides, and also their correlation with the location of the element in the periodic table. So when we talk about acidic and basic oxides, metallic elements typically form basic oxides, and non-metallic elements typically form acidic oxides. So for example, an acidic oxide is an oxide that, when dissolves in water, binds an water molecule and releases a proton to the surrounding solvent. So here an example, CO2 and water forming this molecule, which then can release one proton to water, right? So this is a representation of this process. So here CO2 is an example of an acidic oxide, and an acidic oxide also can react. It can also be defined as an oxide that reacts with an aqueous base, which occurs here in this case too. On the other hand, when we talk basic oxides, is an oxide to which a proton is transferred to when is dissolved in water. So in this case, the basic oxide then releases OH minus to solution when dissolved in water. And then the basic oxide can also react with an acid according to this equation, or according to this transformation. So this acidic and basic acid, this acidic and basic oxide character. So if an oxide has acidic properties, or if an oxide has basicity properties, this correlates actually with other chemical properties. Therefore, a wide range of properties can be predicted based on the knowledge on if the oxide of this element is acid or base. So the correlations follow from the basic oxides being largely ionic, while the acidic oxides are largely covalent. Therefore, elements that forms an acidic oxide will likely to form volatile covalent halides, and an element that forms a basic oxide is likely to form solid ionic halides, for example. So basic oxide will have a more ionic character, and the acidic oxides will have a more covalent character. Therefore, in a way, the acidic or basic character of an oxide can be a chemical indication of whether the element can be regarded as a metal or a non-metal, because metals form basic oxides and non-metal forms acidic oxides. So checking the oxide behavior can give us insights on the nature of the species that we are talking about. And also, An important concept here in this context is the amphoterism, in which the species can act both as a basic oxide or as an acidic oxide. So the frontier between metals and non-metals in the periodic table is characterized by the formation of these amphoteric oxides, and this also varies with the oxidation state of the element. So an amphoteric oxide can react with both acids and bases. For example, aluminum oxide can react with both acids and bases according to these equations as described here. And this behavior of acting as both acid and base which is characteristic of amphoterism, is observed for the lighter elements of group 2 and 13, such as beryllium oxide, aluminum oxide, and gallium oxide, and also observed for some of the D block elements in high oxidation states, such as the molybdenum oxide and vanadium oxide, in which the central atom is very electron withdrawn, and some of the heavier elements of group 14 and 15, right? So here we can see the location of the elements in the different groups forming amphoteric oxides, here shown in white, while here in pink we have the elements forming acidic oxides, and in blue the elements forming basic oxides. So the location of the elements that display amphoterism is right at the frontier between acid and basic oxides. Therefore, these serve as an important guideline to the metallic or non-metallic character of an element. And therefore, the onset or the beginning of this amphoterism correlates with this significant degree of covalent character in the bonds formed by the elements. So we come from ionic to covalent character in this direction. So remember that metallic character increases in this direction, right? So here we have metals. Here we have the metalloids, which are the species that include this frontier region, that includes some of the elements showing this amphoterism, and this is the non-metals region, in which we have predominantly covalent interactions and basic and the formation of acidic oxides. So here is an example of the species that are formed like from the reaction between basic, amphoteric, and acidic oxides with water. So acidic oxides like will generate strong acids, basic oxides, strong bases, and so on. So this is a nice diagram illustrating these changes, these behaviors. And regarding the D block, things are not so easily or not so straightforward, in a way that in the D block, there are differences in which amphoterism can be observed as a function of the oxidation state or the oxidation number of the element. For example, if we look at the left of the D block, from titanium until manganese, the only oxidation state +4 shows amphoteric behavior. More on the right of the D block, amphoterism can occur at lower oxidation numbers 3+ for iron, cobalt, and nickel, and oxidation 2+ for copper and zinc. And then in this case, there is no easy way to predict, but it's important to know that this in the D block is dependent on the oxidation state as well. So this reflects the ability of the metal cation to polarize oxide ions that surround it, to introduce the covalence into the metal oxygen bond. So it's not purely ionic anymore, and then it's covalent as well. And this can give like some of this amphoteric behavior. All right. So next, we will discuss the formation of polyoxo compounds, but I think we have seen many concepts today already. I think it's better that we stop right here and we pick up from here in our next class. So does anyone has like any questions about everything that we discussed today? If not, I suggest you guys to go over the class notes and material again, because there was a lot of concepts that were covered, a lot of descriptive features as well. I also recommend you guys to take a look at the support books that I mentioned about this chapter on acids and bases, because it was very descriptive here in class, but if you take a look afterwards and check the material, it's better to try to understand how these variations occur, and I think it's easier to understand than just try to make sense of these descriptions that were covered here today. So I think you would get easier as you reread the class notes or check the books and go over the homeworks later on. So does anybody have any questions? If not, you guys can always ask questions to me at any time by email or with the feedback forms. And I guess I will see you guys on Friday at 12:15, so that we finish these discussions on acids and bases, and we start a discussion on redox properties. Sounds good? All right, guys. So I will see you guys on Wednesday. Have a nice week, and bye-bye.